Welcome to the NPTEL course on building energy systems and auditing. The new module will start today, the module 6. The module 6 is basically about the life cycle analysis and energy audit. Lecture 26 is on the introduction to life cycle analysis. The first 3 lectures will be on the life cycle analysis and the last 2 lectures will be on building audit. In this lecture on life cycle analysis, we will see the various component of building life cycle analysis. As we all know, almost about 30 to 40% of the primary energy which actually goes into the building sector, and this particular 30 to 40% energy which is actually go inside into the building sector or the built environment, which is held responsible for the 40 to 50% of the emission of greenhouse gases, which is very higher inside. So, our building industry is looking into the way that particular 30 to 40% energy is actually going to consume in a building sector also. From that perspective, if you look into a total life cycle of the building, life cycle in the sense it's a life, like any kind of biological creatures that has a kind of a birth, and then it will grow up and then finally to one day to die down. The building is also look into that perspective from the life cycle energy analysis. So, it has some kind of a construction stage and then its operating stage, and finally one day the building will be not be going to be habited, because it will be may say that it has passes through its actual life and it is beyond some kind of the economical repair or so. So, we have to demolish the building. So, there is a final some kind of energy is required to demolishing the building. So, in this way we can say that in time of construction the lot of energy is required to construct a building. Then it is the operating stage, which is the maximum time frame, maybe 50 years, maybe 80 years. It's operating. So, as we till now discussed in the last 5 lectures, the heat gain, heat losses, is indoor temperature, indoor thermal comfort. To maintain that particular scenario, you require lot of energy to be energy expenditure, and that comes under the operating energy of the building. And the finally the destruction, demolition, it is a very small stage, maybe it required maybe a month or so, not maybe a month sometimes. So, you would demolish that one, you go for a new building construction. So, that will be on after this operation stage, but still it is required some kind of energy. And construction stage is also the period is little high, not like demolition, but of course very small with respect to the operation stage. You may say 1 year, 1.5 year, maybe 2 years is the required for a construction. So, a building life cycle, if you see the building energy life cycle, if you see, we have to actually encounter 3 stages, and the 3 stages will require some kind of the energy to be considered to if you want to consider for the LCE, life cycle energy. That is the embodied energy, which embodied into the building because of there are lot of material, lot of processed material, most of the material are processed material. Even if you use some stones or maybe some kind of a thatch or maybe a mud also, adobe, still you require some amount of energy which is comes from the burning of the fossil fuel. After that OE, the operational energy, and the demolition energy DE. So, the LCE, the life cycle energy, mathematically is the arithmetic summation of the embodied, operational and demolition energy, and that has to be expressed in kilowatt hour. Basically all the units, whatever may be the units you may calculate or estimate, finally that has to be converted to the kilowatt hour. And absolute terms, if you want to see, then we have to divide that huge energy value of kilowatt hour divided by the whole carpet area or the built up area of the building. Maybe the built up area of the building and then it gives you a kilowatt hour meter square or that particular the unit, and then you can actually make that is in absolute terms, or maybe sorry, not the absolute terms, maybe it will be a relative terms. Absolute terms are the kilowatt hour. If I divide in by the square foot area or the square meter area of the built up area, then it will be a relative terms. So, time to time I am going to, I have referred these papers, the Asif, the Ramesh, and also another paper we will see. Those papers are fantastically describe those embodied energy and the operational energy, demolition energy, and total life cycle energy of building sectors also. It is available in the internet, you can download and go through those papers. I have already mentioned over here, it is also given in the list of our references. Embodied energy is the energy utilized during the construction phase of the building. Yes, I have already told you there are some material which we acquire from the market, sometimes we acquire from the industry, but those material has to manufacture somewhere. If I am going to use concrete, I require lot of ingredients of the concrete. I require stone chips, I require sand. This too may be a earth material, but still I have to blast it. So, I have to actually do some kind of a blasting, which actually requires some kind of energy. Then there will be some kind of a processing of the stone chips, it will be transported to my site and that also requires some kind of energy. Similarly, if you take steel, if you take cement, it required lot of energy to produce. Steel required mining, from the mines we required the ores of steel, and then we taken that particular ore to the steel plant. We require lot of heat and melt it, and lot of other things has to be other processes, and then that particular steel is actually usable for the building construction as a TMT bar or any kind of rebars, and then those bars, rebars or steel cross sections, steel structural steel sections are transported from the industries to the various markets, and from the various markets to the site. So, whole process from the mining to my site, it required each and every process, each and every sequence required the energy. So, if you sum it off and divide that by the amount of steel, that may be in kg or maybe in meter cube, if you sum it up, what is the total amount of energy required to produce and manufacture, production and transportation of cement, and by the weight of the cement or the volume of the cement, we may say that much of gigajoule or megajoule of energy per meter cube or per kg is embodied inside the particular material, and I can calculate that one, how much I am using, how much steel I am using, how much concrete I am using, how much bricks I am using, how much aluminum I am using. So, those I can calculate and I can find out what is the embodied energy of my building. So, that is one of the way we will see in the next lecture that how that can be calculated. So, this embodied energy as the flow, that it is raw material mining, then the process of the material, then the material has to be transported. Every time you have to transport, not only once, you have to transport the raw material to the processing industry, the processed material can go to the product packaging also, and then again you need to transport it to the product distributions. So, every stage there are the transportation requirement also. So, embodied energy is now classified into two ways. One is called the initial embodied energy. This energy is this particular initial embodied energy is occurred in the very early stage of the construction. You have to construct a building. So, the very first stage of the construction, new building, when you are going to construct, the energy required for this material point of view, transportation, etc., will be the initial embodied energy. This in second part of the energy embodied energy is called the recurring embodied energy, which you require for the repair. After a construct a building today, you may have to repair the building after 10 years or maybe 15 years or so. Big repair is required, maybe small some touch up repair is required, or some kind of a maintenance touch up is required maybe after 3 to 5 years or so. So, that also should be included as a one type of embodied energy, which is called the recurring embodied energy, and then the whole picture of your the total embodied energy for your whole life of the building, life cycle of the building will be clear. We cannot just only take the initial one. So, we have to think about the recurring one also. So, initial embodied energy, if you see again the same, I have to manufacture it, I have to transport it, and I have to erection. From the erection time also, after transporting it, mixing, for some time welding, sometimes it is lifting from ground to the upper floors. So, you require energy. So, basically we can say this particular the energy, the embodied energy, the initial embodied energy is the E manufacturing, that is the energy required for the manufacture, energy required for the transportation to the site, and the energy required for the construction. This particular the mathematical modeling I have taken from one paper by Dr. K. Adalbert of the Lund University, Sweden. It is a fantastic paper. It is available in the internet, or I can also send you by the forum. So, I have taken that paper, and so many other papers are also taken that paper as the benchmark to model this embodied energy. So, this is the equation for the manufacturing embodied energy, where this small m is the quantity, the total amount of material you required to construct some kind of the building, maybe wall. So, m will be your mortar, m will be your brick, something like that. Wi is the ith, so it is I equal to n 1 to n, that means there are a lot of material required for the construction. So, not only one. So, I1 is for one first material, I2 is the second material. Wi is the wastage factor of the ith material. So, in that paper it is wonderfully mentioned the material, some list of material, and how much is the kilowatt per ton embodied energy, and what is the percentage of the waste, and this total is multiplied with the capital M I, which is your the embodied energy of the material. So, multiplying the kg with the kilojoule or kilowatt hour per ton or per kg will give you finally a kilowatt per hour, kilowatt hour. Similarly, we can do the same way, you can find out the transportation energy also. Only change is that that M I is now replaced with T I into T C, that is the distance travel, because it is the transportation to site. So, how much distance you are travelling d I for suppose the ith material, suppose brick you are collecting from local market. So, maybe 20 kilometers, but maybe the marble you are transporting from the Rajasthan. So, maybe it is 1000 kilometer. So, the d fluctuates, and T C is the amount of the transportation energy. So, if it is the short distance, it is 0.75 it is given. Of course, those values are based on the Sweden perspective, not the Indian perspective or some other countries perspective. So, we need to have our own data bank to do that, but this particular mathematical model formula is fantastic in that way. It has taken care of all the parameters altogether. The third one is the construction energy, the process energy. So, that means P j into capital P j. So, there are j, now it is not I, now it is depend upon the type of construction. So, there are j type of construction. So, j 1 may be mixing, j 2, j equal to 2 may be lifting, something like that. So, how much the amount of materials are under that particular construction type, and what is the impact of that construction as a energy point of view is capital P j, that can be multiplied with each other. So, I can get the value of the construction, the energy required for the construction. So, here in that particular paper also a table has been given for some of the excavations, the crane lifting, the smoothing of the soil. So, how much kilowatt hour per ton of soil or of some material is lifted from one place to another height. So, it is 2 kilowatt hour per meter square is required, energy is required. So, finally, we can find out. So, I have a small problem here I have want to show. So, amount of 2000 ton of concrete is used for a pavement for construction. I am considering 10% of the wastage factor. The ingredients of the concretes are exported from an average distance of 25 kilometer. Let us suppose that is the assumptions, and we have to find out the initial embodied energy of this construction with the following data. The energy required for manufacturing those concrete is 210 kilowatt hour per ton. So, I know how much is the ton, I know how much is the wastage, so I can directly use the first equation and I can find out that the manufacturing the energy is almost about 462,000 kilowatt hour. So, I have this M as the amount of so I think amount of concrete, which is your 2000 ton. Okay, this wastage factor is my 10% and M is given here, this is my M. Okay, so, this is your 210. So, I placed everything over 2010 and this. So, this is the first, but this is the manufacturing. The second data has given for the transportation, conveying the particular thing, and the third one is for the process. So, the second one is the transportation. So, same first part, the material and the wastage is taken into account, 2000 ton and 10% of the wastage of material, but D into T, D is 25 kilometer given assumption and T is given over here. The energy required for the conveyance of the concrete is 0.75 kilowatt hour per ton kilometer. So, 1 ton 1 kilometer, if you want to transport that concrete material or whatever, you require 0.75 kilowatt hour. So, this is your distance kilometer and this is your energy and those. So, finally, this 41250 kilowatt hour is your transportation energy required for this particular construction. The third one is the third component of the initial embodied energy is the E construction, that is the energy required for the construction, which is the 2 multiplier. Just two things, one is the amount of process. So, I have to actually 2000 ton amount of concrete I have to process, I have to mix, I have to lift or whatever. So, that particular process has been mentioned here in the problem sheet is that 40 kilowatt hour per ton is the process of concrete, that much amount of the energy is required for the processing. So, directly I can multiply this 2040. So, the 80,000 kilowatt hour is my total amount of the energy required for this processing or whatever construction processing. So, now I can add these three arithmetically. The first one is the material embodied energy, the second one is the transportation energy and the third one is the process or the construction energy. So, I can find out adding all those three numbers and this is the I think it is 5,83,250 kilowatt hour is the total embodied energy of the material. But please remember that this is for the initial construction of those concrete pavement. We required some time maintenance for that for each and every 5 years down the line. So, the same paper is also provided the embodied energy for recurring purpose. So, it has the renovation energy, manufacturing, renovation, transportation renovation and the construction renovation. So, building will have a lifespan, in the lifespan we will have some kind of a repair, retrofit or something like that. So, we have to take that also into account. So, in that particular paper it is also given this particular formula. So, you see the first part of the formula is remains same as the initial embodied energy formula, material energy, but it has been multiplied with a life of the building divided by the lifespan of the building minus 1. Suppose the life of the building is of your suppose 80 years and the life of that particular material, suppose a concrete or maybe a door or maybe sometimes maybe some kind of the flooring that have maybe 10 years of life. I think here it has been also described as there are two type of life, I have not mentioned, but there may be two type of life. One is the called the life actually the strength point of view. After 10 years the strength of the flooring may vanish or reduce down, or maybe it is so less that it is dangerous to maybe that particular material is a kind of a structural material. So, we have to replace it. So, it is a life of the technical life you may say, and there is another life called the aesthetic life, that may be the paint and all. It may not have that kind of the technical life as such, which can trigger to some kind of a danger or some kind of a life threat, but it may pass through its the aesthetic life. So, maybe some let us suppose for this particular case a particular 80 years of building and the flooring may have a life of 10 years. So, this 80 is the in this equation the last part bracket part is the lifespan of the building is 80, lifespan of the material that the flooring is 10 years minus 1. Why is this minus 1? This is actually 8 minus 1, that means this is equal to 7. Why this minus 1 is that you see you required 8 times changes. Okay. Out of the 8 time operation of those changes, the first one is already included in your the initial embodied energy, right. So, that is why it is always going to be minus 1, because initial embodied energy is taken care of your the flooring, and within the zone of 80 years 7 times you have to change that flooring or whatever, which is having a the lifespan of 10 years over a period of building life of 80 years or so. So, based on that this the lifespan of the building by lifespan of the material minus 1 has been taken into account, and here also there are in that particular paper another table they have given some kind of the lifespan in years. Suppose if you say the parquet flooring, it has 50 years of lifespan. Suppose the water pipes and electrical wires are again having 50 years. So, the painting and the wallpapering is having almost like 10 years or so. Maybe in our country it may be little less because of the dust and other the humidity and other issues. So, like that we can have the different ways of look into it, but the formula goes like that. Next is again the transportation renovation kind of a scenario. Same formula is again added with this D and TC. Here 20 kilometer is assumed to be added extra, because some material can be scrapped and then that can be send it to the disposal site, which may assume to be as a 20 kilometer away from the site or so. But there may be some material we may not actually send it to the disposed area, we may actually use it for some other purpose, or maybe you can dump it very nearby areas or so. So, that is also taken. So, it is comprehensively taken that extra 20 kilometer for waste disposal in this formula, and the construction renovation is also the same, that is some action has to be taken in the time of renovations, and for the actions has to be taken you require some the footprint of the energy. So, the same problem we will continue here. So, let us suppose an amount of 20 ton concrete is used for the periodic renovation of those pavement, considering 10% of the waste. The lifespan of the pavement is 50 years and lifespan of the material is 5 years. So, the thing is that after 5 years I am not going to change whole to 2000 pavement, but 20 tons of pavement, maybe 1% of the there will be some kind of a repair or damage maybe we can found, and those 20 tons of the concrete has to be brought into or manufactured or whatever, I mean have to actually construct. The ingredients are exported from 25 kilometer, sorry, imported from 25 kilometer. Find the recurring embodied energy using those formulas or so. So, now my M is 20, it is reduced to 20, this is 10% of your the wastage is there, and 210 is your the material embodied energy which per ton. So, to manufacture that one, because here also you have to manufacture, but the amount is less, amount is not equal to the your initial embodied energies or so, initial requirement or so. At least for this pavement, maybe for flooring you may require to have whole flooring has to be changed. So, in this case of flooring, in case of painting it is a it is the overall kind of a change, but some repair in the wall, maybe some structural repair, you may not have to change whole lot of structural systems or the material. So, that there are differences. Here in concrete pavement, I am assuming that after 5 years 20 tons are going to be used as a the repair or so. This 50 by 5 is nothing but the 50 years is the life of this pavement, and the 5 years is the periodic interval I am going to repair it minus 1. So, that means this 41,580 kilowatt hour is the manufacture renovation energy required for this particular process. You need to transport this the same equation has been further modified with the as it is proposed by this particular paper, and it was found as 6,682.5 kilowatt hour is the requirement of the transportation energy. Similarly, the process energy is going to be the something like this. Now, one point I want to mention over here. Here we have to take the process is 9 times, because there are 9 times we are going to do it. So, it is 20 into 9, that is 100, 80 tons of the concrete has to be required for those 9 times renovations work. So, your total energy required for the process is your almost about 7200 kilowatt hour or so. And because if you see this 9 comes from this is your 9, is not it? This is your 9, 50 by 5 minus this is your 9, 10 minus 1 is your 9. So, 9 times I am doing the thing repeating, but in this particular formula this 9 is missing. So, I have incorporated that in this particular formula. So, actually 20 tons 9 times, so 180 tons of the work. So, finally, the embodied energy recurring, I think there is a small mistake, this is should be typological, this should be R. Embodied energy recurring will be your 55,462.5 kilowatt hour. So, if I go to the next, if I go to the next, so this is going to be the end of this lecture, but if I go to little earlier, so what I feel is what I got here is the almost 5,83,250 is the initial embodied energy, 5 lakh, please remember 5,83,000, and here it is what I am getting is that it is 55,400. Of course, it is because of the 20 tons only, and there it was much higher, 2,000 or 2,000 ton. So, of course, the initial embodied energy will be much higher with respect to the recurring one. So, we will carry forward this particular calculations recurring and initial embodied energy in the next lecture, which is the lecture number 28. 28 will again see how this two will be actually linked with the operational energies also. So, we will see that. So, what we discussed over here is the building life cycle components, and we have seen that what are the fundamental evaluation method of the initial and the recurring embodied energy. So, I will go back to the reference section again. So, all the papers which I have referred here is mentioned, those Asif's paper, Ramesh paper and the Adelbarth paper, and we can actually go through this, and you can have more knowledge on the embodied energy calculations and this mapping. Thank you very much.